Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, I would like to tell you all that we would be conducting two sessions on carboxylic acids derivatives. One session we are going to conduct today and the another session later on, that is in near future, we would be conducting. And dear friends, I would like to tell you all that for this very session, that is on carboxylic acids derivatives, today we have with us in our studios Dr. K.K. Arora. Dr. K.K. Arora is Associate Professor in Department of Chemistry, Zakir Hussain Delhi College, University of Delhi. As you all know that Dr. Arora keep visiting us, and with the help of this EduSet platform, he delivers lectures only for you, so that it becomes convenient for you to study the course material, the material sometimes which you are unable to study through your books. I hope that the way he used to give examples, these examples help you in understanding the topic. So taking this lecture forward, I would first of all like to welcome our guest, Dr. K.K. Arora. Dr. Arora, welcome to the EduSet lecture. So today we are going to discuss about the carboxylic acid derivatives. So over to you, sir.
Thank you. Hello viewers, and welcome to this session on carboxylic acid derivatives. We have discussed earlier about the carboxylic acids. Today we will discuss about certain group of compounds which are obtained from carboxylic acids, and we call them as carboxylic acid derivatives. We will discuss today that what are these carboxylic acid derivatives. Then we will talk about the nomenclature, and we will take up amongst these acid derivatives acid chlorides, amides, esters and acid anhydrides. Then we will talk about one reaction, that is nucleophilic acyl substitution. Although this reaction is one of the properties of carboxylic acid derivatives, but we will discuss it here because this is a reaction which is also used for the interconversion of these acid derivatives. So before discussing the properties, we will talk about this reaction briefly here. Then based on this reaction, we will talk about the stability of acid derivatives. We will talk about the preparation of these acid derivatives, that is acid chloride, amides, esters and acid anhydrides. And then finally we will summarize our today's work. As I said that we have already discussed about carboxylic acids. This formula represents carboxylic acid. This C double bond OH is the functional group. And when this OH group is substituted by some other group, we get the compounds, they are called acid derivatives. Now carboxylic acids may have different substitution on this side also. If it is some alkyl group, these are aliphatic carboxylic acids, and they may have different substituent like amino group, amino acids, halogen group, halo acids, hydroxy group, hydroxy acids and so on. But specifically when we discuss this carboxylic acid derivatives, we talk about the group of compounds which are obtained by the substitution of this OH group. And in most of the derivative formation, actually this OH, I will not say it has been substituted, actually this OH group and some other compound, they eliminate a water molecule, and that group comes at the place of this OH. Such as if this OH is replaced by Cl, we get this group of compounds, we call them as acid chlorides or acyl chlorides. Now although these acid chlorides are not obtained by reaction with HCl and the loss of water molecule between the two, but we can consider it as if that Cl has come here when its reaction is there with HCl and one water molecule is being lost. Then next group of compounds, we call them as amides. Amides also can also be considered as there has been a loss of water molecule between this carboxylic functional group and ammonia. NH2 group comes here, we call them as amides. Then next class of compounds is esters. Esters are formed when a water molecule is being lost between this acid and some alcohol or phenol. So there remains the OR dash. This R dash, if it is aliphatic, then this some alcohol group, and if it is some aromatic group, means it is some phenol group. Then we get acid anhydrides, which are obtained by the loss of a water molecule between two carboxylic acids, which may be same or different. So, all these compounds, that is acid chlorides, amides, esters and acid anhydrides, they are classified as carboxylic acid derivatives. In place of chlorine, there can be bromine or iodine also. So, there can be common group of compounds called acid halides, but most commonly used and generally synthesized for different purposes are mostly acid chlorides. That is why we are specifically taking here acid chlorides. Now, let us talk about the nomenclature of these one by one. This represents the formula for some acid chloride, RC double bond O Cl. In the common system of nomenclature as well as in IUPAC system of nomenclature for naming these acid chlorides, the ending in the acid, ic acid, is replaced by il chloride. Whether it is a common name for the acid or the IUPAC name for the acid, the ending ic and acid, this suffix is replaced by another suffix, we call it as il chloride. We will see it with the help of some examples, such as let us take the simple acid CH3COOH, which is commonly known as acetic acid, and its IUPAC name is ethanoic acid. When this OH gets substituted by Cl, we get this acyl halide. The formula for this is CH3COCl. Now, while naming this compound, we have to replace ic acid. The common name is acetic acid, and in place of IC and acid we put YL chloride. So, name for this compound becomes acetyl chloride, and when its IUPAC name is considered, it is ethanoic acid. Then again the IC and acid, ic acid part is replaced by YL chloride. So, the name for this acid chloride becomes ethanoyl chloride. Since the IUPAC name for all the acids ends in oic acid, so the name of the acid halide will be oil halide. For chlorides it will be oil chloride. Let us take some more examples. Ethanoic acid, propanoic acid, butanoic acid. When the OH of these acids is substituted by Cl, the acid chlorides that we get, they have this formula: CH3COCl from ethanoic acid, CH3CH2COCl from propanoic acid, and CH3CH2CH2COCl from butanoic acid. Now, they will be named as ethanoic is replaced by YL, so name becomes ethanoyl and then chloride. This will be propano YL, so propanoyl chloride. This will be butano and then YL and chloride, so butanoyl chlorides. So, the names for these three acid chlorides are respectively ethanoyl chloride, propanoyl chloride and butanoyl chloride. Let us take one more example. This is a 4 carbon acid. So, it is butanoic acid, and when the OH is substituted by Cl, the name for this compound becomes butanoyl chloride. But suppose we want to name it according to common system, this acid is called normal butyric acid. So, it will become normal butyryl chloride. So, its IUPAC name is butanoyl chloride and common name is normal butyryl chloride. Similarly, for this acid is again a 4 carbon acid, but one of the methyl is present as a substituent. So, the longest chain is of 3 carbon. So, when we want to name it according to IUPAC system, it is 2-methyl propanoic acid and OH is replaced by Cl. So, it becomes 2-methyl propanoyl chloride, and common name for this will be isobutyryl chloride, because this acid from which this has been obtained is commonly known as isobutyric acid. Then we can get acid chlorides even from the aromatic acids, such as this is the chloride from benzoic acid. The OH of the benzoic acid is replaced by this Cl. So, this is named as benzoyl chloride. This is some substituted aromatic acid. This is benzoyl chloride in which a nitro group is present. So, the numbering in the ring remains the same as the main functional group carrying carbon is assigned position 1, and then we number the ring in clockwise or anti-clockwise direction, so that the substituent gets the lowest number. In this case, it is present at para position, which will be number 4 from any side, 1, 2, 3, 4, or from this side 1, 2, 3, 4. So, this is named as 4-nitrobenzoyl chloride. This is a saturated 5 carbon compound cyclopentane, and its acid that has been converted into acid chloride. So, this will be named as cyclopentane carbonyl chloride. We call this a cyclopentane carbonyl chloride, and if it is a 6 carbon chain, then ring, then it is similarly named as cyclohexane carbonyl chloride. So, this way we can name the saturated cyclic acid derivatives or aromatic acid derivatives. Then next we take up amides. Amides, as said, the OH is replaced by this NH2 group. These compounds are called amides. While naming amides, the ending ic acid in the common system is replaced by the suffix amide, and in IUPAC nomenclature the suffix oic acid is replaced by amide. So, in both the cases the ending is amide, but in common system IC acid is replaced, whereas in IUPAC nomenclature oic acid part is replaced from the name of the corresponding acid from which this amide has been obtained. Again, let us take some example, such as this is the amide from 1 carbon acid. 1 carbon acid is methanoic acid. So, its IUPAC name for this amide is methanamide, and commonly this acid, when it is OH here, is formic acid. So, the common name for this amide is formamide, means formic acid. So, ic acid part is replaced by amide, methanoic acid, oic acid part is replaced by amide. Similarly, if we have a 2 carbon acid, this is commonly known as acetic acid and IUPAC name is ethanoic acid. So, according to IUPAC system, its name is ethanamide, oic acid part is replaced, and common name is acetamide, ic acid part is replaced from acetic acid. So, it is acetamide according to the common system. Similarly, if it is a 3 carbon acid, its IUPAC name is propanoic acid, a common name is propionic acid, and the corresponding amide which is obtained, it is named as propanamide, IUPAC name, propionamide, common name. So, this way amides are named, but amides may not be simply substituted by NH2 group. This H might have some other substituents, and then according to that amides are classified as primary amide when it is simple NH2. If one of the H has been substituted by some alkyl group, means this amide is obtained by the reaction of the acid with some amine, then this is called secondary amide, and if both the hydrogens are substituted by alkyl groups, then this amide is called tertiary amide. Like amines, those nitrogen which have all the 3 alkyl groups, we call them as tertiary amines. Here 2 are alkyl groups on nitrogen and 1 is this acyl group. This functional group is amide, and this compound is classified as tertiary amide when 1 alkyl group secondary amide, and when no alkyl group we call them as primary amides. Then for naming these secondary or tertiary amides, the alkyl group which is attached to nitrogen is named as N-alkyl before the name of the amide. Whether it is the common system or IUPAC system, we will write a capital N and then name of the alkyl group. This is just to indicate that this alkyl group is attached to the nitrogen of amide, such as this compound. This is CH3CO. Suppose in place of this OH was there, this is ethanoic acid. If it is simple NH2, then it is ethanamide. but it is not, it is that ethanamide where one hydrogen has been substituted by methyl group. So, its name becomes N-methyl ethanamide. This will be IUPAC name, and commonly the corresponding acid is acetic acid, then amide will be acetamide, and it is having one methyl group. So, according to common system, this is named as N-methyl acetamide. Let us take another example. It is a 3 carbon acid, IUPAC name propanoic acid, amide propanamide, and now this amide has got one ethyl group in place of hydrogen, which is attached to this nitrogen. So, it is named as N-ethyl propanamide. This is IUPAC name, and common name will be propionic acid, then corresponding amide is propionamide. So, in common system it will be named as N-ethyl propionamide. Let us take one example, say propionamide. If it is mono substituted, that is corresponding secondary amide, this is N-methyl propanamide. If both the nitrogen they get substituted, there are 2 methyl groups, then we will name it as NN dimethyl propanamide. If the substituents are same, then we write 2 times N, and then we write that name of that alkyl group prefixed with the term di, indicating that there are 2 groups. But suppose these groups are different, then they are named in a different way. I will take one example. This is an amide from the aromatic acid, benzoic acid. So, this will be named as benzamide. If one of the hydrogen is substituted by methyl of this amine part, this will be named as N-methyl benzamide. If there are 2 different substituents on this nitrogen, one is methyl and one is ethyl, then we will have to write the name of both the alkyl groups, which is prefixed by the capital N, and then these groups are written in alphabetical order. Say this is ethyl starting with E, this is methyl starting with M. So, we will write ethyl first, then methyl, then benzamide, and ethyl and methyl both are prefixed by capital N. So, the name for this compound becomes N-ethyl N-methyl benzamide. Suppose there is a substitution in the ring. So, the basic name for this compound is benzamide, and there is a methyl group substituted at position number 1, 2, 3. So, we name this compound as 3-methyl benzamide. We can name this compound also as a derivative of the acid which has got a common name. If it is carboxyl group here and methyl group at position number 3, which is the meta position, then commonly that acid is also known as metatoluic acid, and then we can consider it as a amide from metatoluic acid, then this is commonly named as metatoluamide. Then amides can be cyclic also. Cyclic means the compound that we have, as I talked about amino acids, the amino present in the alkyl chain may form a ring and form the amide with the carboxyl group of the same molecule. We call them as cyclic amides, and these are named as lactams. And the position of this amino group and the position at which the ring is being formed is represented by a Greek letter like beta, gamma, delta, as we see in the examples. This can be considered as the amide obtained from a 3 carbon acid. This was originally say carboxyl group, this is CH2, then CH2 and then NH2 here. So, it must be propanoic acid having amino group at the 3 position 1, 2, 3, and in common system this is named as alpha beta position. So, we can say that it is beta amino propionic acid that has cyclized the NH2 of the same molecule has reacted with the carboxyl and formed the ring here, and common name for this compound then becomes beta propiolactam. Lactam word indicates it is a cyclic amide, beta indicates the position of the NH2 group where it has formed the linked. So, it is alpha, it is beta position, right, and propio indicates the name of the starting acid, that it was a 3 carbon acid. So, common name for this lactam is beta propio lactam, whereas IUPAC names for these compounds are derived from some other cyclic compounds, like this is known as azitidine 2-one. This compound without C double bond O is azitidine, and then there is position number 2 having carbonyl. So, IUPAC name is azitidine 2-one. These lactams are more popularly known by their common names because their IUPAC names are bit difficult. Is a 5-membered lactam. Now, if you consider this as the carbon 1 of the carboxyl, and according to common system, this is alpha position, this is beta position, this is gamma position. So, it was a butyric acid having amino group at the gamma position, which has formed the cyclic amide, that is lactam, and that is why this is named as gamma butyrolactam. For IUPAC name, this is considered as a derivative of a 5 carbon heterocyclic compound pyrrole, and the double bonds are reduced, it becomes pyrrolidine, and then there is a carbonyl at carbon number 2. So, this is named as pyrrolidine 2-one. A 6-membered lactam, again in common system, this is alpha position, this is beta, gamma and delta. It means the position for the amino group on the chain of the acid was delta. It is a 5 carbon acid, 1, 2, 3, 4, 5. So, valeric acid which has formed this lactam, and this is named as delta valurolactam. And in IUPAC system, this is considered as a derivative of pyridine, and when it is reduced, it is piperidine, and it is named as piperidine 2-one. So, these are the common names and IUPAC names for cyclic amides. Then a very common compound, NH2CONH2, urea. This can also be considered as amide. It is having CONH2 group, and one of its common name is carbamide. It is named as carbamide because it is the amide of another acid called carbamic acid. This acid, this is COH group, and it has formed the amide here. So, from name carbamic acid, the name for this compound is derived as carbamide. Carbamic acid itself is the amide of another acid which is called carbonic acid. So, on this side this amide has been formed, and carbonic acid, you know, is the solution of carbon dioxide in water. So, when carbon dioxide under pressure dissolved in water gives carbonic acid, and its diamide is urea. Then let us take up next esters. Esters are the compounds where this OH has been replaced by the part from alcohol or phenol, and in common system of nomenclature as well as in the IUPAC system, they are named as alkanoate. The ending of the ic acid, alkanoic acid, ic acid part is replaced by ate, and before this we name this part. It may be an alkyl group or phenyl group, whatsoever it is preceded by this name. So, let us take some example. Say this is an acid, a 1 carbon acid HC double bond OO, that is methanoic acid, or common name is formic acid, and here this is methanol. So, methanol has reacted with methanoic acid to give this ester, and for naming this ester we will take this alkyl group first, that is methyl, then name of the acid, and ending of the acid is changed into ate. So, methyl methanoate, methanoic acid, ic acid replaced by ate. So, it becomes methyl methanoate, and in common system we will call it as methyl formate because common name is formic acid. So, IUPAC name is methyl methanoate and common name is methyl formate. This is again an ester between methanol and a 2 carbon acid, that is ethanoic acid or acetic acid. So, IUPAC name for this will be methyl ethanoate and common name would be methyl acetate, methyl ethanoate, methyl acetate. Now, this is ethyl group here, means this is ester with ethanol and is a 1 carbon acid, that is methanoic acid or formic acid. So, this will be named as ethyl methanoate or ethyl formate, common name is ethyl formate. And this is a 2 carbon acid, ethanoic acid or acetic acid, and then its ethanol portion, ethyl group. So, we will call this compound as ethyl ethanoate in the IUPAC system and ethyl acetate in common system. So, this way esters are named. If we have the esters from aromatic acids, say this is the ester from benzoic acid with methanol. So, this will be simply named as methyl benzoate and its IUPAC name or common name both will be same. Then this acid. Now, while naming these aromatic compounds, we have to be very careful to see that which part is aromatic. It is acid part or the phenolic part. In this structure, we see that actually acid part is this CH3COO, this part is acid part and this is the phenol part from where it has come. So, this will be named as phenyl and then ethanoate or phenyl acetate. So, IUPAC name is phenyl ethanoate, common name phenyl acetate. And this is we find an ethyl group here and then a 3 carbon acid, propionic acid. So, common name will be ethyl propionate and IUPAC name will be ethyl propanoate. Then esters can also be cyclic. The cyclic esters can be formed from the hydroxy acid. On the alkyl chain, if there is some hydroxyl group, it may form the ring by reacting with the carboxyl group. And these cyclic esters are named as lactones. And again, the position of this hydroxyl group or the oxygen present on the chain is represented by the Greek letter alpha, beta, gamma, delta, etc. Such as this is the lactone which is formed from the hydroxy acid where hydroxyl is present at the beta position. This is alpha position, this is beta position. So, this is named as beta propiolactone because it is a 3 carbon acid 1, 2, 3. So, propionic acid, hydroxyl was present at beta position which has formed the lactone, that is cyclic ester. So, we indicate beta as the position for oxygen and then we write lactone. So, it becomes beta propiolactone. The IUPAC name for this compound is oxetane 2-one. Then a 5 carbon ring structure gamma butyrolactone because it is a 4 carbon acid butyric acid which has formed the lactone and alpha beta gamma, it is the gamma position where hydroxyl group was present originally, now indicating the position of the oxygen. And in IUPAC system it is named as a derivative of 5-membered oxygen heterocyclic compound called furan. So, it is dihydrofuran 2,3H one. 2 indicates the position of one and 3H indicates that it is 1 hydrogen and then a double bond is also reduced. And this is named as delta valirolactone, that is 5 carbon acid, linkage of oxygen through a delta carbon, and in IUPAC system it is considered as a derivative of a 6-membered heterocyclic compound containing oxygen which is named as pyran and it is named as tetrahydro 2H pyran 2-one. Anhydrides. Anhydrides, as I said before, are the compounds which are obtained by the loss of water molecule between 2 carboxylic acids. These are anhydrides. Now, these anhydrides may be from same acids or they may be formed from different acids. If this R1 and R2 they are identical, they are same, it means this anhydride is from the same acid and such anhydrides are classified as symmetrical anhydrides. If this R1 and R2 groups are different, then we call them as unsymmetrical or mixed anhydride. And for naming these acids, if it is symmetrical anhydride, we name the name of the corresponding acid once, but if it is an unsymmetrical anhydride, then we name both the acids. Let us take the examples. Say this is the anhydride which is formed from methanoic acid or formic acid, HCOOH and then HCOOH. Here water has been lost between the two hydroxyl groups. So, this is called methanoic anhydride or formic anhydride. Similarly, if it is from acetic acid, it is called ethanoic anhydride or acetic anhydride. This is a 3 carbon acid giving the anhydride, propanoic anhydride. Then benzoic acid forming the anhydride, we call this as benzoic anhydride, because this is an anhydride between 2 benzoic acid molecules. Now, if there are 2 different acids, say it is the anhydride from benzoic acid and ethanoic acid, then we have to name both the acids, and these acids are written in alphabetical order. So, benzoic starts with B, whereas ethanoic starts with E. So, we will write its name as benzoic ethanoic anhydride, and in this case it is propanoic acid, this is ethanoic acid. Now, ethanoic will be written first because it starts with E, propanoic starts with P. So, this is ethanoic propanoic anhydride. Then we can get anhydrides even from the dicarboxylic acids, where in the same compound 2 carboxyl groups are present at a suitable position so that they can eliminate water and form anhydride, like succinic acid. The 2 carboxyl of the succinic acid may eliminate water to give this compound called succinic anhydride. Similarly, if the 2 carboxyl in the phthalic acid they eliminate water, we get this compound called phthalic anhydride. So, this is about the nomenclature of these acid derivatives. Now, let us talk about one reaction which I said that although it is a property, but we have to discuss it because this is very important in discussing the preparation of the acid derivatives as well as their interconversions and their stability. Now, these are acid derivatives, this is a general formula where Y can be different groups like Cl for acid chloride, NH2 for amides, OR for esters, etc. This carbonyl group is having the partial negative charge on oxygen and partial positive charge on carbon due to difference in the electronegativity of carbon and oxygen. Now, this Y group, whatsoever this group is, can create its influence by inductive effect as well as by resonance effect. By inductive effect, all these groups which are present, that is Cl in acid chlorides, nitrogen in amides, oxygen in anhydrides as well as in esters, are more electronegative than carbon. So, they have an electron withdrawing influence, and if they withdraw electron, they enhance the positive charge on this carbon. So, by inductive effect, these groups enhance the positive charge on this carbon. But if this group can take part in resonance using the lone pair of electron, then this lone pair of electron will be involved in resonance like this, and since the electrons are shared from this Y group towards this carbonyl, the positive charge on this carbon will be reduced. So, resonance effect and inductive effect, they are creating opposite effect. Inductive effect is increasing the delta positive charge and resonance effect is reducing it. Now, we are talking about nucleophilic substitution. A nucleophile will attack this carbon more effectively if the positive charge is more. It means those groups where this Y is more electron withdrawing, that is more electronegative and less participation by resonance, will be easily attacked by the nucleophile. And if the nucleophile attacks here and this Y group is substituted, then we call it as nucleophilic acyl substitution, because the remaining portion after the loss of this Y group, RCO, is called as acyl group, and then that acyl group is attached to the nucleophilic part that has attacked this molecule. Now, this substitution may occur provided the attacking group is a stronger base than the leaving group. So, Y is any leaving group as I discussed, and this Z is a nucleophile. First step will be that it attacks here, pair of electron will move towards oxygen, and when this electron pair comes back, then from this carbon either Y may be lost or the Z may be lost. If Y is lost, Y is removed, means if Y is a weaker base than Z, then obviously the substitution has occurred and we have obtained the product in which Y has been substituted by Z. Z is our nucleophile and this nucleophilic substitution has occurred. But if Y is a stronger base and Z was a weaker base, then first this attack will be slow, and even if this attack has occurred, when this electron pair comes back, this Z will be lost back and we will get starting compound. So, it means this substitution can occur by those nucleophiles only which are stronger base than the Y group which is already present. And if we see these groups, all of these can be substituted by water. Hydroxyl group will be replacing this Cl in acid chlorides, this OR in esters, OCOR in anhydrides and NH2 in amides. This water may be used as such, or the rate of the reaction is enhanced when it is catalyzed by some base. We call this as a hydrolysis reaction. So, hydroxide ion is sufficiently strong base to replace all these. So, all these groups can be substituted by hydroxide ion. But if we consider with each other, that suppose I take acid chloride and react with ammonia, or I take some amide and treat it with HCl, then what will happen? Now, that will depend upon that which is the stronger base. This is the acid derivative that we have, and the leaving group in acid chloride will be Cl minus, in anhydride will be OCOR with minus charge on oxygen, in alcohol or phenols it will be OR with a negative charge on oxygen, and in case of amide it will be amide ion minus NH2. Now, out of these, whichsoever is a stronger base, that will have less tendency to leave and it will have higher tendency to attack. Now, what we find as we move from chloride to this OCOCR, then OR and NH2, we find that their basicity increases. This is more basic, this is less basic, right. So, that will show that this is opposite to their reactivity, because this group is a strong base, it has a very less tendency to lose, it means it is less reactive, and chloride ion is giving the group that is coming out is a weaker base, means can be easily replaced. So, it is more reactive, and from this sequence we can also get the idea that acid chloride can only be obtained from acids by some other reagents, but acid chlorides can be converted into acids on hydrolysis, to amides on reaction with ammonia, they can be converted into esters or even to anhydrides. Whereas, anhydride which comes second in the series can be converted into amides, can be converted into esters, but they cannot be converted back into acid chlorides. So, just by looking at this sequence we can get the idea, this gives us the idea about the methods for the preparation as well as their stability and reactivity. We will talk about more about these reactions while discussing their preparation and properties individually. Let us take about the methods for the preparation of acid chlorides. Carboxylic acids can be converted into acid chlorides on treatment with the reagents like thionyl chloride or phosphorus pentachloride or phosphorus trichloride. When the reaction with thionyl chloride, then the byproducts are sulfur dioxide and HCl, both are gases, and this is considered as the best method for preparing acid chlorides from acids, because if we take the calculated amount of acids and thionyl chloride, then these two are the gases, they will be lost and we will get pure acid chlorides. Although we generally use PCl5 or PCl3 which are easy to work upon. Then how this reaction actually occurs with these reagents, because as I said that there are no chloride ions which can replace the hydroxyl group. Actually, when the reaction is carried out with thionyl chloride SOCl2, it is one of the oxygen of this carboxylic acid, maybe this or this, acting as nucleophile, they attack the sulfur. sulfur is having sufficient delta positive charge because it is attached to 3 electronegative atoms, chlorine, chlorine and 1 oxygen, and when it is attacked here, this electron pair shift towards oxygen. Then these electron pair when comes back, then one of the chlorine is lost, and while chlorine is going away, it takes away this hydrogen. So, this can go as HCl, and this pair of electron comes back to oxygen. Then in the next step, a chloride ion may be from the reaction mixture, that has been lost as HCl, or it may be the chlorine of the same molecule itself. As we have studied in SNI type of mechanism, it is the chlorine of the same molecule. They may attack this carbon and pair of electron goes here. Here I have shown with this chlorine attacks, this pair of electron goes there, and if this is chloride is not there, it will be this chlorine with the lone pair of electron attacking here. Then a cyclic intermediate will be formed, and when this pair of electron comes back, then this is lost as sulfur dioxide and this is lost as chloride, and that takes away the hydrogen which is already there from where this Cl minus had come. So, we get RCOCl, that is acid chloride, sulfur dioxide, and HCl is lost. So, this is the mechanism for this reaction. It is very much related to SNI type of reaction by which alcohols are converted into alkyl chlorides. Then a similar mechanism operates when the reaction with PCl5 is there. Here this one of the oxygen acting as nucleophile attacks the phosphorus, which is having sufficient positive charge because it attached to 5 electronegative chlorine atoms. Then when pair of electron comes here to the phosphorus, one of the chlorine is lost as chloride. Then this chloride takes away this hydrogen, this pair of electron comes back to oxygen, and then we get this intermediate which is not very stable because oxygen is linked to phosphorus with 4 chlorine. Then one of the chlorine again either from the reaction mixture as chloride ion or the chlorine from the molecule itself, this may attack here on this oxygen. This is just shown the previous stage when it is protonated oxygen, Cl minus ion are there, or we can see Cl minus ion is already there. The Cl minus attacks here, or it may be Cl from the molecule itself which attacks here. Pair of electrons goes there, and when this pair of electrons they come back, then this bond breaks and this is lost as POCl3. One more chlorine is lost, that takes away this hydrogen. So, one of the side product is POCl3 and then RCOCl is formed, acid chlorides are obtained. And a similar reaction occurs even with phosphorus trichloride. One of the oxygen acting as nucleophile attacks this phosphorus, one of the chloride is lost, then this chloride may attack back, and ultimately we will get P, 2Cl and 1 OH on the phosphorus as the side product. But the benefit of using PCl3 is that this may be further attacked by another molecule of acid, one more chlorine is substituted and then a third molecule, third Cl is substituted, ultimately this gets converted into phosphoric acid. So, one molecule of PCl3 can convert 3 molecules of acid into acid chlorides. So, that is the benefit of using phosphorus trichloride. The same reagents can also be used for preparing acid chlorides from the aromatic acids like benzoic acid also. The same PCl3, PCl5 or thionyl chloride can convert it into benzoyl chloride. Then aromatic acid chlorides can also be obtained by using phosgene as one of the reagent. Benzene reacts with phosgene in presence of aluminum chloride to give this C6H5COCl, that is benzoyl chloride. This reaction is you can say related to Friedel-Crafts acylation. In Friedel-Crafts acylation we have RCOCl in presence of aluminum chloride. Here it is C double bond O and then 2 Cl, one of the Cl has been substituted and COCl group has attached here. Then preparation of acid amides. Acid amides can be obtained from carboxylic acids. As a first step, these carboxylic acids, when they are treated with ammonia gas, they form a salt called ammonium carboxylate, that is ammonium salts of the acids are being formed. These ammonium salts on heating strongly lose a water molecule and get converted into amides. So, this is one of the very simple method of getting amides from carboxylic acids, that they are basically treated with ammonia under pressure at high temperature. So, in the same vessel, in the same step, initially the ammonium salts are formed, which get converted into amides. Then another method, that amides can be obtained from acid chlorides. As I said before, that acid chlorides are such compounds which are susceptible to attack by any of these bases, and Cl is easiest to remove. So, acid chlorides are useful intermediates for making all other acid derivatives. So, ammonia gas acts as a nucleophile, and basically in these two steps substitutes the Cl. In first step, the electron pair goes here, and when this electron pair comes here, this Cl is lost as Cl minus, and while leaving it takes away H from this NH3 portion that was there, and we will get corresponding amides. If in place of ammonia we use some amine, here also nitrogen has a pair of electron and it can act as nucleophile. So, when the amines are treated with some acid chlorides, we will get in a similar manner as the reaction of ammonia had occurred, the corresponding amides, which will be having the substituent present here will be present here. So, we will get secondary amides. The reaction proceeds exactly in the same way. This is acting as nucleophile, attacks here, pair of electron goes to oxygen. When this pair of electron comes back, one of the Cl is lost, and while leaving it takes away the H plus from here and is lost as HCl. So, we get a substituted amide. Similarly, if we treat any acid chloride with a secondary amine, we will get here the tertiary amides. So, this is a good method using acid chloride, any type of amides. Like this is a propanamine, when it is treated with ethanoyl chloride. So, this NH2 will substitute this Cl and we will get N-propyl ethanamide, because acid portion will be this much CH3CO. So, amide will be considered from acid. The nomenclature is as a acid derivative. So, it is ethanamide, and this propyl group is present on the nitrogen. So, it is named as N-propyl ethanamide. When both these units, that is acid chlorides as well as the alcoholic part, that is we have phenol, they can react at a very fast rate in presence of sodium hydroxide, and it is a name reaction called Schotten-Baumann reaction. Like aromatic amine, ammonia, this aniline, and then benzoyl chloride, they react, we will get corresponding amide, that is benzenylide. So, when both the units are aromatic, reaction can be carried out in presence of NaOH. This reaction is very fast and named as Schotten-Baumann reaction. As I said before, because that will come actually in esters, if in place of this aniline we have phenol, the similar reaction will occur, only difference will be here we will be getting the corresponding aromatic ester. Then we can get acid amides by the reaction of ammonia with acid anhydrides also. As I said before, because ammonia is a strong base and amides can be obtained from all the three acid derivatives, that is acid chlorides, acid anhydrides and esters. So, when ammonia reacts with acid anhydrides and the molecule breaks, then we also call this as ammonolysis. When lysis means cleavage, when any bond is cleaved with the help of water, we call it as hydrolysis. Here we are cleaving the bond with the help of ammonia, that is why we call it as ammonolysis, and ammonolysis can occur on acid anhydrides as well as on esters. This is the reaction with anhydride, the bond breaks, NH2 comes here, H will go here, and this will be lost as acid molecule. Similarly, if we have some ester, this bond will be cleaved, NH2 will come with this, we will get amide, and this portion will be lost as the alcohol that was present in ester. Then amides can also be obtained by the partial hydrolysis of cyanides. Cyanides are the compounds having carbon nitrogen triple bond. When they are partially hydrolyzed, that is one of the pi bond is cleaved, then what happens? hydrogen of the water goes to nitrogen and OH comes to carbon, and this OH and there is a C double bond N between nitrogen. So, this is an enol type of structure. So, it undergoes tautomerism and we get our C double bond O NH2, that is from here the OH was there, H goes to nitrogen and pi electron shift here. So, we get amides. If we will hydrolyze it completely, we will get carboxylic acids. So, that is why we are using the term partial hydrolysis of cyanides. Then anhydrides, they are obtained sorry, it has happened here. Anhydrides, they can be obtained from the carboxylic acids by the loss of water between two acid molecules, and generally for removing these water molecules we need a dehydrating agent like phosphorus pentaoxide. So, when carboxylic acids are heated with P2O5, they lose the water molecule and we get corresponding anhydrides. And if we have this type of carboxylic acids which have two carboxylic group on them, that is dicarboxylic acids, and they are suitably placed, they on simple heating lose a water molecule, like succinic acid will give succinic anhydride, or phthalic acid on heating again loses water molecule and we get phthalic anhydride. Then acid anhydrides can also be obtained by the reaction of carboxylic acid using a compound called ketene. Ketene is this compound, CH2 double bond C double bond O, but in this case we will get only those type of acid anhydrides which on one side will have the 2 carbon acid part, that is the acetic acid part, and the another side it can be any alkyl group, like this any carboxylic acid reacts with the ketene. Reaction proceeds like this, that OH bond cleaves, H goes to this carbon and this oxygen part goes to this carbon. So, it becomes RCOO, right, and then again CO CH3. So, this is the part coming from ketene and this is the acid part. So, we can get all those acid anhydrides which on one side are the anhydrides from acetic acid and on another side there is some other acid. So, mixed anhydride can be obtained. Then mixed anhydride can also be obtained by treating acids with acid chlorides. We can have acid chloride or different acid reacting with some different carboxylic acid. They can lose a molecule of HCl, and when we want to remove a molecule of HCl, obviously we need some base, generally pyridine or some other tertiary amine is used, and we get acid anhydrides. We can get anhydrides also on reaction with sodium salts of carboxylic acid with acid chlorides. They on reaction just a molecule of sodium chloride gets precipitated and anhydrides are formed. These two methods are used for making symmetrical anhydrides as well as for mixed anhydrides. Then preparation of esters. Esters, as I said, are obtained by the loss of water molecule between some alcohol or phenol and carboxylic acid. So, we can use directly carboxylic acid and alcohol and water molecule is to be removed. This reaction is generally carried out in presence of few drops of sulfuric acid and this ester is obtained, such as if ethanoic acid is treated with ethanol, then a water molecule is lost and we get ethyl ethanoate. This reaction proceeds again in such a way that alcohol part acts as a nucleophile. It attacks on this protonated acid part. The acid is used as catalyst and it protonates the oxygen first, which enhances the positive charge on this carbon. Then this H plus is lost and in the final step ultimately a water molecule is lost. You can see that all these steps I have written as an equilibrium reaction. Actually, this reaction may go in the forward direction as well as in the backward direction. In the forward direction, we are using one acid molecule, one alcohol molecule in presence of acid, whereas for the backward direction, we have ester which can be treated with water and we will get back this, that will be hydrolysis. In the forward direction, one water molecule is to be lost. And this reaction proceeds in the forward direction when water is continuously removed from the reaction mixture, otherwise we will not get the full yield of ester. Our higher yield of the ester can be obtained when we use one of the reagents, either acid or alcohol, in excess, as we have studied in Le-Chatelier principle. Then alcohols and phenols can also react with acid chlorides to form esters. That reaction occurs again in presence of a base like pyridine or any other tertiary amine, because it requires the loss of a molecule of HCl. So, this is an alcohol or phenol may react with acid chloride, we get esters. This is a phenol and we are getting phenyl ethanoate. As I said earlier, if we take some acid chloride also, which is aromatic acid chloride like benzoyl chloride, then that reaction will be the example of Schotten-Baumann reaction. Then benzoyl chloride can also react with ethanol and we get ethyl benzoate, or other cyclic acid chlorides similarly react with this to form corresponding esters. Any alcohol may react with even anhydrides to give corresponding esters. And one example here is the aspirin, which is obtained by the reaction of acetic anhydride with salicylic acid, which acts as phenol. Here the reaction occurs in presence of sulfuric acid. Then silver salts of carboxylic acids can also react with alkyl halides, and a loss of silver bromide occurs and we can get esters. Then ethers can also condense with carbon monoxide in presence of boron trifluoride to give esters. And there is a reaction, Tishenko reaction, which we have studied in aldehyde. In presence of aluminum alkoxide, alcohols also react to give esters in one step. And diazomethane can also be used for the preparation of esters. Diazomethane gives the CH2 group, which gets introduced between O and H, and we can get methyl esters only. So, today we have discussed about the nomenclature and the methods for the preparation of these acid derivatives. In our next session, we will talk about their physical and chemical properties. Thank you.
Definitely, we would be discussing on the properties later on in our next session. Till then, take care and keep studying this lecture. We would be going to upload this lecture on YouTube very soon, so that you can access this lecture number of times you wanted. Thank you, sir. Thank you so very much.